Hello, in this video I want to go over mergesort. Mergesort is a recursive function. It runs in big O n log n. It's considered better than insertion sort and selection sort and bubble sort, but it's considered slightly less favorable than quicksort. And the reason for that is because quicksort has an advantage that allows you to sort the array in place rather. And mergesort will have to do a little more lifting, so to speak. It'll have to do a little bit more work by creating additional arrays using a merge function. And before I get into the actual algorithm, I want to go over what I've written so far. So I have an example up here, and I'll explain how the merge function works and how the subarrays are created up here. I have basic C headers, the input, output, and math for infinity. I'll explain what the infinity is for. Down here, I have my four declarations, merge, sort, merge, and the naive merge. I'll go over my naive merge algorithm really quick and then just copy it into the merge algorithm and explain why the naive merge doesn't work. And then the print array function is pretty self-explanatory, just prints the values of the array. In my main function, I have an array. I have 8 values, could be any number of values, but I put this together, just for this example. And the values are obviously not sorted. I'm using C, so I put the length here. I have a length of 8. And print, and then the naive merge. Right now, naive merge does nothing, and I'll explain the merge sort in a little bit. And yeah, so I'll run this really quick. And you can see nothing really happens. I have a 996523, 9965, and nothing happens. It just prints the values of the array. Okay, so the way the merge sort function works is there's two important functions. There's the merge sort, which performs the recursion, and then the merge function, which actually merges the subarrays together. Before I actually go over merge sort, I want to go over merge, and then I'll explain how the merge sort works. So the way you could look at the merge function is you have a starting indice we'll call P because that's the invention. You have a pivot, which is half the size of the array, which is Q, and then you have a length of the array, which is R. The way you do the merge function is you split the grand array, the original array, into a left and right array. So over here, this is the left array, and over here, this is the right array. And you split it using the P, Q, and R values. For this example, I'll assume P is equal to 0, Q will be half the size of the array, and R will be the length of the array. Sometimes it might not be, and I'll show that in a little bit. But for this example, I'll assume you just have a left array and a right array. So the way the merge function works is you split the original array into left and right array, and then you compare the left values with the right values. You have 3 counter variables, I, J, and K. K is for the original array, I is for the left array, and J is for the right array. And it should say right size. And the reason we have infinity is so we don't index outside the bounds of the array. So what we do when we start is all the I, J, and K values are set equal to 0, and we count from K equals 0 up to R. We compare the left value at I, which is in this case is 99, with the right value at J, which is 3, which is smaller, well 3. Then we increment J equals 1, and we continue to do that. So 13 and 99, so it would be 13. 19 and 99, 19 rather. 73 and 99, well 73 in this example. And you can see this is where infinity comes in, because now we're comparing infinity with 99, and obviously 99 is going to be less than infinity. If we didn't have that infinity there, we'd essentially be comparing, we would actually go outside the boundaries of the array. So every time we do a comparison, if the comparison in one of the arrays, in this case the right array, is smaller, we increment that respective counter. If it was left, we'd increment I. Since it's the right array that is smaller, we increment J, so we end up counting all the way to right size. And the reason for that is because this value is 99. If I change this to something else like 3, then we would essentially be comparing the I value, and then we would insert this and increment I to 1 and so forth. So let me write that down so you can see what's actually going on. And this is for the merge function. I haven't even gone over merge sort yet. This is just merge. And I'm going to put in the naive part, and I'm going to run it, and you can see why the naive part doesn't work, and then I'll show you why merge sort is necessary. So you can assume that Q is equal to 4 and P is equal to 0, so left side is equal to 4. Once again, r is equal to 8 in this example, and then q is equal to 4. So left and right are size of 4, which is what I just showed you. When we construct the array, we need to have it one size larger for the infinities. Okay, so now we have our left and right arrays, and we'll put the infinity in right now. Now the infinity macro in C is a double value, so we cast it to an int, and it ends up being the largest integer value, which is more than enough than we need. I could just as well pick 1,000, and that would be an infinity for this example. Okay, now I fill up left and right arrays from the original array. Start at P. Now the right array. Okay, so now I filled up the left and right array, and I'll print these really quick. Make sure everything works. Warning, 75, what did I do? Ah, forgot my equals. And then should just be another warning. Okay, I didn't use K yet. Okay, so what does this look like? Uh-oh, one of these is not correct. It's good to check really quick. So the left array looks right, 9965, and the right array is all butchered. So I definitely did something wrong in the right array. Make sure I clear this up. J equals... This should be 0, although it doesn't change anything because p is equal to 0. I don't know if I showed the function call, but 0, and then q is just the pivot. It's halfway, so it's halfway from 0 to the length. So in this case, p is equal to 0. Ah, that's definitely wrong. So j is left than right sized. Now we should run it. Okay, that looks right. So you can see up here the left array is right here, and then the right array is right here. And it matches up. Perfect. And then the infinities. I could just as well actually print out the infinity just so you can see it's the largest integer value. Make sure it all works. Yep, and there's the largest integer value. So I'll comment these out and now merge them into the original array. Once again, this isn't going to work, but I'll just copy and paste this into our merge function up here and then call mergesort and it'll work correctly. So reset the counter variables, and k equals 0 for, I guess I didn't need to reset k. K is less than r plus k, don't want to make any errors. And compare if Now remember, when you increment at the end of the variable, it will return the variable I and then increment afterwards. This just saves some space. I could just write in another line. Else right is less than left I. Let's see what we got. And the out array is 313, which is obviously wrong still, but I just want to show you that it ends up being the comparison between. So it essentially becomes the left array, 313, 19, 73, and then 99, 65, 23, and 76, and we didn't compare infinity. So you're probably saying to me, well, what's the point? This is obviously wrong. Well, the point is we have to sort the subarrays. So what I'm going to do is I'm going to copy this here into the merge algorithm. At this point it's exactly the same. And then I'm going to call mergesort. The trick behind mergesort is a recursive function call that splits the array into a subarray. So I'll comment that out, and we'll make 8 recursive function calls because we're splitting into 8 subarrays. So essentially what we're going to end up doing is we split this down from a left array and a right array into another left array, another right array, and then another left array and right array until we have 8 of these, and then we compare these. So we compare left and right again, just like we did up here. This is exactly the same. This is what the merge function is doing. We compare 65, 99. We compare 23 and 76. Looks good. 3 and 13, 1973. Okay, so now the left array becomes 65, 99. Wait, am I doing this right? Yeah, I think so. So actually, wait, we compare 60. So we're looking at, it's getting a little bit sloppy, but if I move this over, we're comparing these. So this would be I and this will be j. This is in the merge function now. We compare these. So this would actually be 23 rather. I almost screwed that up. And then we increment this. So we would now be comparing 76 and 65. So this becomes 65. And then, let's see, what 23. So now we're comparing 99 and 76. So this becomes 76. So now at this point, you could imagine there's an infinity here, because this is the merge function. There's an infinity. There was always an infinity. Even in the single array, there's an infinity. So we compare infinity and 99. And now this is definitely sorted, 23, 65, 76, 99. This is, kind of cool. And then we compare 3 and 13, obviously good. Then we increment. So I is equal to 1, 13, and then 19. So obviously that bumps up. And of course we have our infinity here. And it's a little bit sloppy, but compare 19 and infinity. Obviously 19 is less, 73 and infinity, and bam, that's sorted. Okay, so what's the big deal? So now we're comparing these again. And we compare 3 and 23, okay, 13 and 23, okay, 19 and 23, okay, we compare 73 and 23, okay, well that's, 23 is less than 73, and now we're comparing infinities, no, not yet, never mind, sorry, we compare 65 and 73, 65, compare 76 and 73, 73, now we're comparing infinities, we're comparing 76 and infinity, 76 is less, 99 and infinity, bam, sorted array. So let's run this. Okay, so let's see, where am I at? Where's my main function? Okay, so mergesort. So when we call mergesort, just to recap, we recursively split this. So we start with 0 and we start with the length. Is p less than the length? It's yes. So then we create a pivot. In this case, it would be 4 on the first function call, would be 4. And then we mergesort 0 through 4, mergesort q plus 1, which would be 5 up to the length of the array, create the right subarray, and then we merge. And we continue to call, actually I shouldn't say we merge yet, we continue to call mergesort again and again until we split down into these individual subarrays. So that, I may have screwed up the explanation because we don't call merge until we're done calling mergesort, because that's part of the recursion. Our base case is right here, making sure that the starting indice is less than the length of the array. So let me make sure everything's set up. And now the final moment. Warning, didn't use that variable. And it did not work. Why did it not work? Did I screw something up here? Let me check. Let me see my master code really quick. Should be right. P plus I. I might have screwed this part up. No, it's still not right. Just keep looking. Oh, this is what I forgot to do. K equals P. I probably didn't need to move the infinity. And there we go. Sorry for that error. And it's obviously sorted. 3, 13, 19, 23, 65, 73, and 76. Yeah, make sure you start at P. I forgot to do that. In my naive example, it didn't matter because I wasn't making any recursive function calls. But up here, the P value will change. And that's the recursion up here. And I can comment this out really quick just to show you the number of calls as well, which is originally what I wanted to do. And you can see 8 calls and see the p-value changes. So that's where I had screwed up. So that's mergesort, and it has a running time of big O n log n. And the reason for the log n is because the mergesort splits it in half, and then the merge function runs in log n. And this is the log n part right here.